before starting any event. I request the technical team to kindly play the AV.
असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्युर्मामृतं गमय ॐ शान्ति शान्ति शान्तिः या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा.
Thank you, sir. Now I request Honorable Chancellor and Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalaya to facilitate the virtual welcome of Honorable Chief Guest Dr. Apurva Khare. Thank you, sir. Now, to pay tribute to this extraordinary genius, we are proud to present a short documentary. We hope to delve into the brilliance of Ramanujan and draw inspiration from his history of perseverance, creativity, and passion for knowledge. I request the technical team to kindly play the AV.
Srinivasa Ramanujan. Srinivasa Ramanujan, one of India's greatest mathematician geniuses, was born in 1887 in Erode in Tamil Nadu, India. He is recognized as one of the greatest mathematicians of his time, but Srinivasa Ramanujan had almost no formal training in math. He was the second Indian to be inducted as a Fellow of the Royal Society, which is a fellowship of some of the world's most eminent scientists. He joined the fellowship in 1918 at the age of 31 as one of the youngest fellows in the history of the society. He compiled 3,900 results, which were mostly identities and equations, before he lost his life at the age of 32. His infinite series for pi was one of his more celebrated findings. There is also a museum dedicated to telling Ramanujan's life story. This is located in Chennai. His birth anniversary, December 22, is celebrated as a National Mathematical Day every year. Ramanujan worked on divergent series. He sent 120 theorems on implied divisibility properties of the partition function. He gave a meaning to Eulerian second integrals for all values of n, negative, positive, and fractional. Ramanujan made substantial contributions to the analytical theory of numbers and worked on elliptical functions, continued fractions, and infinite fractions. In 1990, he began on his own on mathematics, summing geometric and arithmetic series. Goldbach's conjecture is one of the important illustrations of Ramanujan's contribution towards the proof of the conjecture. The statement is that every integer greater than 2 is the sum of 2 primes. For example, 6 is 3 plus 3. Ramanujan and his associates had shown that every larger integer could be written as the sum of at most 4. Example, 43 is equal to 2 plus 5 plus 17 plus 19. Partition of whole numbers. The partition of whole numbers is another problem that captured Ramanujan's attention. Ramanujan also developed a formula for the partition of any number, which can be made to yield the required result by a series of successive approximations. Example, 3 is equal to 3 plus 0 is equal to 1 plus 2 is equal to 1 plus 1 plus 1. Ramanujan also studied the highly composite numbers, which are recognized as the opposite of prime numbers. He studied their structure, distribution, and special forms. The Fermat theorem. Ramanujan also did considerable work on the unresolved Fermat theorem, which states that a prime number of the form 4m plus 1 is the sum of two squares. Ramanujan number 1729 is the Ramanujan number is the smallest number which can be of two cubes in two different ways. 1729 is equal to 1 cubed plus 12 cubed is equal to 9 cubed plus 10 cubed. Cubic equations and quadratic equations. Ramanujan showed how to solve cubic equations in 1902, and he went on to find his own method of solving quadratic equations. Euler's constant. By 1904, Ramanujan had begun to undertake deep research. He investigated the series of 1 by n and calculated Euler's constant to 15 decimal places. Hypogeometric series. Ramanujan also worked on hypogeometric series and investigated relations between integrals and series. He was to discover later that he had been functions. Ramanujan's own work on partial sums and products of hypergeometric series have led to major development in the topic.
Thank you, sir. Now I request Honorable Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalay, Dr. Upinder Dhar, to deliver welcome address on this occasion. Over to you, sir.
Good afternoon to all of you. Today's distinguished speaker, Dr. Apurva Khare, all deans, directors, faculty, and my dear students. One of the unique features of our university is to invite those scholars who have contributed significantly. And also on the special occasions when we have various orations. We thought of orations in the name of great sons of the soil, starting with Aryabhat Memorial Oration, then followed by C.V. Raman Oration, Vikram Sarabhai Oration, and so on. In that series, Srinivasa Ramanujan Memorial Oration is also organized every year. Normally we do it on 22nd of December. And since 22nd was falling on Sunday this time, so we are having it on 23rd of December. As we have seen just now in the documentary, that Ramanujan's contributions are very well known, particularly to the mathematicians. But our intention is that every student, irrespective of the discipline, should know. Because what happens, unfortunately, what is happening for last few decades in our country, students believe that all great things have been done in the West. We are only following what has happened in the Western countries or, say, developed countries, which is a myth. So we want to know our students that it is not true. It is not a reality. Sons and daughters of this nation, this soil, have also contributed in various disciplines, and they are known for their work, and we need to appreciate it, we need to celebrate it. Though it is well known that scholar does not belong to a particular country. The aura of a scholar goes beyond the political boundaries of a nation. Knowledge doesn't know such boundaries. Therefore, students need to understand this. So we have been inviting people who have really made contribution. Their names are found in the textbooks. But when such people speak to students about their contributions, students start really believing. So when students read certain things from the certain contributions in the textbook, they half believe. But when they hear from the horse's mouth, that makes them to believe. For example, when Anil Kakodkar was invited first time, he shared his experiences of Pokhran because he was part of the team. When Mashelkar came, he talked about the patenting, how patenting is important, how it came into the picture. When Kasturi Rangan visited our campus, so he spoke about his experience about the space science. So such stalwarts have been coming. Intention is to help students to be grounded and appreciate and celebrate the works of the nation, works of the sons and daughters of the nation, scientists and those who are in other fields. So in that light, today we are having this Srinivasa Ramanujan oration, and we are very happy that Dr. Apurva Khare has accepted our request and he is today with us. In fact, for this Ramanujan oration in past, we had people from TIFR and Indian Institute of Science. Dr. Khare is also from Indian Institute of Science, so we welcome him once again. And I'm sure that this session will be a very happy learning session for all of us, because learning is a continued journey. So we have to keep on learning from each other, irrespective of the discipline. Our national education policy also emphasizes on multidisciplinary approach. We should not have the boundaries. Disciplines should not become boundaries. A person of physics should not think that, well, why should I talk about chemistry? And a person of chemistry should not feel that, why should I learn mathematics? Such boundaries are artificial. We have to remove such boundaries. Ultimately, knowledge and wisdom. Knowledge can be converted into wisdom when we don't have such boundaries. So we have another opportunity today to learn from a young scholar. I would say young from my age and background. Apurva is very young. So once again, I welcome you, Apurva, to this session. Thank you very much.
Thank you very much, sir, for this valuable information and enriching address. We are honored with the gracious presence of our chief guest, Dr. Apur Khare, IISc Bangalore. To read the citation, I invite coordinator of today's program, Dr. Satish Shukla.
Thank you, Ashaman. It is a great privilege for me to read the citation for Dr. Khare. I quote, Dr. Apur Khare is a faculty of mathematics at the Indian Institute of Science, Bangalore, and a member of the Analysis and Probability Research Group. Dr. Khare did his schooling in Bhubaneswar, Odisha, at Demonstration Multipurpose School and Bakshi Jagbandhu Vidyadhar College. He obtained B State from the Indian Statistical Institute at Kolkata and MS and PhD in mathematics from the University of Chicago. He then held postdoctoral positions at the University of California at Riverside and Yale University and a research associateship at Stanford University. Dr. Apur Khare has contributed to matrix positivity in analysis, combinatorics, and discrete mathematics and representation theory. Dr. Khare was awarded the Santi Swarup Bhatnagar Prize for Science and Technology, the highest science award in India for the year 2022 in mathematical sciences. Besides the Bhatnagar Prize, he also received the Swarna Jayanti Fellowship and the Ramanujan Fellowship from SERBDST Government of India. He was invited to deliver the 2022 Hansraj Gupta Memorial Award lecture and received the A.K. Agarwal Award 2023 by the Indian Mathematical Society. Dr. Khare has been elected as a Fellow of the Indian Academy of Sciences. In a publication by the Government of India celebrating 75 years of Indian independence, he was listed as one of the 75 scientists aged under 50 who are shaping today's India. He also delivered a plenary talk at the 2023 AMS Joint Mathematics Meetings in Boston, USA. Shri Vaishnav Vidyapith Vishwavidyalaya Indore is privileged to present this citation to Dr. Apurva Khare during the 7th Srinivasa Ramanujan Memorial Oration as distinguished speaker on 23rd December 2024. Unquote. Thank you, ma'am.
Thank you, sir. Thank you, sir. I would like to request Honorable Chancellor and Vice Chancellor Shri Vaishnav Vidyapith Vishwavidyalaya to present virtual citation to our chief guest Dr. Apurva Khare. Thank you, sir. Now I feel honored to invite Dr. Apur Khare to address the gathering. Welcome, sir.
Okay, thank you so much for inviting me and for all the very kind remarks. And the Professor Dhar's comments are, of course, very valuable as well. It is, yeah, of course, today is the birthday we celebrate of Srinivasa Ramanujan, but even before him, there were many greats of mathematics and many fundamental works in mathematics that were carried out in India, which even the West is slowly starting to take note of. So there is for example, there is a series formula for pi, which was earlier called Leibniz series after Leibniz, who was a contemporary of Newton in the medieval times. But nowadays it is starting to be called the Madhava Leibniz series in honor of Madhava, who was much earlier, and so on. So there are things that are slowly starting to be recognized, and hopefully we will keep, we will keep appreciating more and more the contributions of older Indian mathematicians. At the same time, there are many leading mathematicians in the world today who are of Indian origin or from India itself, and I hope this continues for a long time. So today I want to talk to you about some very simple mathematics. So the word divisibility was mentioned, although not in this context, in the work of Ramanujan in the video. And so today I want to talk to you about some basic experiments. I want to sort of tell maybe the students here that mathematics is not something very theoretical and complicated. Of course, it can be, but it can also be sort of very simple. And it is at its basic heart the idea of trying to find patterns. At least that is how, as a kid, I started out in mathematics by trying to find patterns in things. And actually, in some sense, this story has an Indore connection because both my parents are from Indore. So I, as a child, have gone there maybe after the age of 9 or 10 for the next 10 years until college. I would spend every summer at least 6 weeks in Indore with my relatives. My uncles, both my uncles still stay there. My aunt also does. So yeah, so I have a lot of cousins in Indore, or had, and still have relatives in Indore. And it was in one of those summer holidays when I was in class, I think 11, or yeah, 11 class 11 summer holidays, that the story that I will tell you today started. And so it's really there is an Indore connection as well. So I will not use slides. I will use the board. So let me maybe first point it here and ask if you can see the board clearly. maybe I'll just write something here, just draw some. And these are visible to everybody. Professor Pathak.
Sir, it is slightly visible.
Now it is better.
Mhm. No, sir.
Oh. Where is it visible? Not
Okay. Yes, sir.
visible. Okay, fine.
It's visible, sir.
Okay, thanks. Okay, so maybe I'll sorry. So what I want to talk to you about is sort of uh, divisibility test for any number. So it's not very complex, and that's the thing I want to say. This came out of my trying to find patterns, but then one has to establish some, and one has to prove that these things work, these formulas, these recipes work, and so that is the story of that is what I want to tell you. So so basically here is, let me start with something that we have all seen. Suppose I want to say, is the number 361 divisible by 9? Right? And we know how to solve this question. The answer is you just look at 3 plus 6 plus 1 and you ask if this sum is divisible by 9. And since this sum is not divisible by 9, therefore 361 is also not divisible by 9. The same thing is, the same thing is true for, say, let's see, the same thing is true for, sorry, I'm just going to pin this so I can see that I can see that how big and all the screen appear. Okay, the same thing is true for test by 3. Of course, you add up the digits of 3, 6, and 1 by 3, and if that answer is divisible by 3, then yes. If not, then no. How about for 11? So is 361 divisible by 11? This also we have seen in schools, and the answer is again. The answer is no, because this time you take the alternating sum and difference. Okay? And now this is this divisible by 11? Well, this is 3 minus 2 minus 2. This is not divisible by 11, so therefore neither is 361. Okay, great. So this is what one does for very simple things. Okay, fine. Please tell me, I should say, Professor Pathak, when I have maybe like 5 minutes left or something. So then I will. Okay, so so these tests are very well known from school, and the question that sort of one can naturally ask is, how about other numbers? Is there a divisibility test like this for 13, for 7, or for 361 itself? You can divide a number by 361. So so I, again, as I said, I was actually in Indore, and in my uncle's place, there was this book by Shakuntala Devi. I used to read different kinds of books, and there was this book called Mathematical Games or some fun to remember, or I forget what the name was. Anyway, it was there, and so I was going through it, and I came across this test for 19. Now that is something that we definitely do not see in schools. A test for 19. Okay. And here is the test. You look at, say, 361, that's why I chose 361. And so normally now, how does one write down 361? Right? As we all know, 361 you write down using place value. So this is equal to what? It is 1 times 1 plus 6 times 10 plus 3 times 100. 100 I will write as 10 squared. 10 to the 1, and 1 is just 10 to the 0. Okay? This is what it is. This is, you write it down using the place values, and you go from left to right in increasing powers of 10. So the first digit, the rightmost digit is 10 to the 0, that's the unit digit. The next one is the tens digit, and then the 100. And you can, of course, write larger numbers as well. So the test for 19 goes the other way. So this is by Shakuntala, mentioned in the book of Shakuntala Devi. another mathematician from India whose name sort of made it, became somewhat famous in the West. And her test was the following. She said, look at 361 and go from left to right. So if we go from right to left, I multiply the number by powers of 10. This time she said multiply the digits by powers of 2. So some magic, there's some reason why maybe. So you from this you form the number 3 times 2 to the 0, powers of 6 times 2 to the 1, plus 1 times 2 to the 2. And add up these products. Okay, what do you get? You get 3 plus 12 plus 4, and you get 19. And the test is if this next number is divisible by 19, then so is the original number. Otherwise, they are both not divisible. That's the test. Now, if you notice, the summation here is also, in some sense, the same kind of thing as this. The summation here, so this is sort of a test that goes left to right. This is the usual number that goes right to left. In this case of sum of digits, you can write down 361 as again going from left to right. This is 3 times 1 to the 0. Here you just are adding up the number, that means you are multiplying by 1. So the test for 3. The test for 11 similarly. 11, I could do the same thing. I could say 3 times 1 to the 0 minus 6. Let me write the minus 6 as 6 times minus 1 to the 1 plus 1 times again 1. So plus 1 minus 1 plus 1, alternating sum and difference. But plus 1 is also minus 1 square. It's not just 1 square, it's minus 1 square. And so for 3, 9, 11, we already had tests that were going sort of, that were adding numbers up, but that can also be thought of in the fashion of this test for 19. So when I saw this test by Shakuntala Devi for 19, I realized that the test for 9 and 3 and 11, which we have seen in school, we have seen in school in class 7 or 8 or maybe earlier, I forget now. But we have seen all these tests and they involve adding or subtracting, but they can also be thought of as exactly the same kind. So what I noticed was this pattern. So as I said, this is why mathematics, just at a very abstract level, can be sort of very theoretical and so on. But concretely, if I want to understand some phenomena, the nice thing is to just understand the patterns. And so here is a pattern. Here is one phenomena, she said, Shakuntala Devi pointed out, which turned out to then suddenly say, well, look, all the things we have seen earlier are parts of the same pattern. And now you can ask, is there such a test for 9? There is a test for 19, 11, 3 and 9. Right? So maybe I can write a table. So divide by and powers of. Right? So I want to divide by 3 or 9. I look at powers of 1 and I add them up from there. Left to right, powers of. If I want to divide by 3 or by 9, the powers of 1. For 11, the powers of, what did I say? Minus 1. For 19, powers of 2. And you can ask, how about other numbers? If I say 7, or if I say, maybe I'll say 21, what number goes here? Or if I say 29, what number goes here? So one can ask simple questions like this. What is the pattern that these 4 numbers give me that works here? And that was the mystery that I was trying to solve. So as a high school student, I tried to see could I find a pattern and could I then use the pattern to predict. It's not enough to find a pattern that accounts for all the given data. You have to use the pattern or your theory. The real test of a theory in science, in all kinds of science, whether physics, chemistry, wherever, once you have a hypothesis, once you have a working model, the real test of that model is to actually go ahead and predict. So can I explain all the other number divisibilities? Right? And so that's the story I want to tell you. Right? And so how does one try to find the common pattern? Yeah, so for my I recorded all the data, so I can erase all these things. So rather than doing this now, I will just, what I want to do is for 3 and for 9, for 3 or for 9, I want to say I want to go this way. This means I want to take it to 3 times 1 to the 0, plus 6 times 1 to 1, plus 1 times 1. That's the pattern for this. This is the pattern for with minus ones and then. Okay. Okay. So these were the basic things like 3, 9, 11, and 19. Let me tell you that again now. So let me tell you there is a pattern. So first of all, let me tell you there is a pattern. So don't worry, there is a pattern, and that's exactly the story there. But before that, recently, maybe I should come up. Maybe okay, fine. I'll start by telling you the pattern for 29. And then we'll try to figure out what this pattern is doing. Right? Okay, so for 29, the pattern is that you use 3 instead of 2. This is 3. So what does that mean? It means that suppose I want to do, let's say, 891. Okay, sorry, 899 for fun. Is this divisible by 29? So from here I go. So I take 899 in the left to right direction, and that gives me, by using 3, it gives me 8 times 3 to the 0 plus 9 times 3 to the 1 plus 9 times 3 to the 2. How much is this? Let's see. It's so it is 8 times 3 is 8 plus 27 plus 81. That is 108, 116. Now this is still maybe too large a number to check. Is this so? What the test says is that this number is divisible by 29, then this number is divisible, and if not, then it is not. They are together divisible or none. So but now again this number is sort of too large, so let's make it better. So I take so 116. And that's the point. You don't need to stop just once. If you get a large number, you run the test again. 116 gives me what is 1 times 3 to the 0 plus 1 times 3 to the 1 plus 6 times 3 to the 2. Right? 29, yeah. How much is this? This is 1 plus 3 plus 54 is 58. And if you still want to go one more time, other than saying, like, I know 29 times 2 is 58, but if I don't want to even think that much, then let's do this one third time. 58 is, sorry, this goes to 5 times 3 to the 0 plus 8 times 3 to the 1, which is 5 plus, which is, sorry, yeah, 5 plus 24 is 29. And now because 29 is divisible by 29, therefore so is 58, therefore so is 116, therefore so is 899. Okay, so there is a pattern. You can do this and you can try for, if you tried 898, you would check that you don't get the number. You would get 115 probably, or you would get 112, and then you can check again that it doesn't. So this test seems to work. Now why? What is going on, right? So how did one come up with 3 or 9 or something like that? So this, and again now let me come back to the theme that we have discussed. It started from Dr. Dhar's comment as well, that there are all these ancient mathematical contributions of which we are just starting to understand stuff. So Shakuntala Devi in particular, she knew a lot of this ancient mathematics under the name of Vedic mathematics. So in fact, Vedic mathematics has a lot of very interesting. They give us a lot of different sutras, so different recipes for how to multiply quickly, or how to add quickly, or how to like carry out division or square a number. They have all kinds of. Maybe I should call them algorithms. Maybe I should call them recipes. No, they have all kinds of yeah. One can call them tricks, but tricks would sort of indicate that you are not meant to know how these things work. They're like magic tricks. But no, the ancient people definitely knew how these things work. They recorded these things in the form of verses because storing information on paper or that kind of thing was hard. It passed from word of mouth from teacher to student. But this kind of thing does feature. And in fact, there is a name called. So I'll give you a book actually in which this thing is mentioned. So so first of all, what is that? The question is what is the pattern? And let us make it more precise. So again, when you do science, you have to state things very precisely. Let's call this number so divide by d. That is a black pen maybe. So we are going to the divisor. What we divide by is going to be called as d, and the powers of the number here will be called k or just k. Okay. So given the number d, I want the number k so that you go from left to right, multiplying by increasing powers of k, the digits. When you added those products, if that number is smaller, is divisible by d, then so is the original number. That's really what we are doing. The question is, what is the pattern? Given the d, so given d, what is k? Or what is KD? Or even if there is no formula for it, is there an algorithm? Is there a recipe to calculate this number? And we see this, so again, we started from something very basic, what we see in schools. And then we go to something that we don't see in schools. This was in a book by Shakuntala Devi. But then you can try and play around, as I was actually doing in Indore one summer, almost 30 years back now. It's quite a long time ago. But yeah, and one finds patterns. So let me first of all tell you one more number, and then you will see a pattern. Okay? Let me put in one more number. And then you will already see a pattern, hopefully, which is let's say 13. And in that case, it's very so now let's try to figure out what the pattern. Okay, so for 9, we said the number was multiplied by powers of 1. Okay. For 19, let me call it 0, 9. Okay. For 19, the powers were 2. For 29, the powers were 3. Okay, so this was again, let me remind you, this is the notation for this is the number we are dividing by, this is the number whose powers we take. Which means that, for example, I want to find out if 0, 9 is divisible by 9. What do I do from here? I get 0 times 1, anything power 0, plus 9 times 1 power 1. Okay. 1 9 was 1 times 1, 2 power 0, plus 9 times 2 power 1. Okay. 29 similarly, well, guess what? It is 1 times, sorry, this is 2 times 3 power 0 plus 9 times 3 power 1. So what we are really saying is, it's really the multiplication table of 9 that's happening. All these numbers just contribute 0, 1 or 2 because we are multiplying by 1. So now I can ask, so for example, if I say 79, right? Now it's very easy to guess the pattern, at least for numbers you want to divide by, whose unit digit is 9. Right? So what is this? So somebody in this audience, maybe some student is there online, you want to tell me the answer? What is that number? Anyone? And so if you just see here, it's really just one more than the 10th digit. Right? And so this is going to be the pattern, at least for numbers ending with 9, whose last digit is 9. How about if I want to do 129? Well, again, here I will do 13. And I can check that 129, this is divisible by 90 by 129, which it is, if and only if I replace 1 times, now it starts getting very large, that's the only thing, right? So, but let's see. 1 times 13 power 0 plus 2 times 13 power 1, that's 1, plus 9 times 13 square. And you can check. So check this is, it's a very large number, but check that this does work. I will leave it as like as a homework to you if you want to check that. For 129, that test does. Okay. And so let me try to explain now why this test works. Let me just do it for the numbers ending with 9. But let me try to explain why. The point is, we have some recipe. We thought of some recipe. We found some pattern. And so for every given number like this one, maybe for this number, we can verify the pattern. But what if I give you 157? Is this divisible by 129? Of course, the answer is no. But does this test also fail? How do you verify if something fails or works? Right? That's the goal. The goal is that you have found some test. One has found a working hypothesis, but one has to check that the working hypothesis applies to all the known or all the possible phenomena. Right? And that is why, for example, Newton's theory of gravity is so amazing, because it applies not just to an apple falling onto the ground. It applies to planets between themselves. It applies to sun and the planet, the moon and the earth. It applies to stars, binary stars in some big galaxy or something, or some star orbiting some black hole. It applies to all kinds of phenomena. Newton's theory. Of course, for very large and heavy objects, one has to then take Einstein's theory to upgrade it. But at a fundamental level, up to some non-relativistic verifications and so on, Newton's theory works pretty well, and it has been experimentally verified. But the amazing part is Newton's realization that it is not just the apple falling onto the ground that can be explained. That one theory accounts for everything in the whole universe, at least in the observable universe, maybe. Right? So this is what we have, a theory, we have a pattern that seems to work for each individual operation. We want to ask if this works in complete generality, if it works for all possible numbers which end with 9. And of course, there are infinitely many numbers which end with 9. I can't keep verifying calculation for each of infinitely many numbers. That will take infinite time. Of course, we want to do this in finite time. And this is where the power of variables comes in. So let me just quickly mention a couple of things about variables, and then we will go back to this kind of to verifying whether this works in general using the power of variables. Variables are what we all know: x and y and n and m and so on. These are what are symbols which actually represent some number or some integer or some decimal number. But these are, but we can say that each of them can represent any number. The idea is that we want to use them to represent any number, like any decimal number typically for these guys, any integer, a counting number, whole number for these guys. So for example, suppose I want to say the following. Suppose here's the question, right? So multiply for an example, 2 consecutive odd numbers. Suppose I tell you this and add 1. Multiply 2 consecutive odd numbers like 5 and 7 or 13 and 15 and add 1. You always get a perfect square. Always get a perfect square. That is the claim. I am saying that this is always true. You might have read books where they say, here is a magic trick with which you can amuse or amaze your friends at a party. This is a magic trick. Now, I will not erase the pattern. Keep it. Why is this true? So let us check. Let us check that it works. Okay, fine. So, I mean, it works because, for example, so for instance, let's say 1 times 3 plus 1. So this is just 4, which is 2 squared. You can say 7 times 9 plus 1, which is 64, which is 8 squared. I could even do negative numbers. Minus 5 times minus 7 plus 1, which is 36, which is 6 square. But of course, I'm going to call it minus 6 square. And now what is the pattern? Of course, it's a square. But not only that, you know the number of which it's a square. 2 is a number between 1 and 3. 8 is a number between 7 and 9. And that's why I use minus 6. It's the number between minus 5 and minus 7. So that's the idea. We have a common pattern. But I can't keep verifying this for every single infinitely many odd numbers, right? 1 times 3, 3 times 5, 5 times 7, 7 times 9. I can't keep doing that. So I have to have there has to be a way in mathematics for us to verify infinitely many of these calculations in finite time. So can we verify? Can one verify? And of course, this is science. So I can verify, or you can verify, or someone else can verify. It has to be replicable. Right? Science always is replicable. You have to, whatever I do, I can't just say I did it magically. Now I don't care if you do it or not. No, I will give you a recipe that you can do it on your end, and you will still get the same calculations that I do, because that's, again, that is what science is. So can when I verify all of these, all infinitely many of these in finite time. I don't know if this is true for all infinitely many unless I verify it. I have to verify for myself, right? I don't believe it on somebody's word of faith. I'm going to verify this. And the answer is yes. Yes, by a single calculation. Not just finite calculations, but one calculation will do it, right? And I think this we all have seen. But let me still show it to you. That's the whole point of variables, right? The calculation is very simple. I have odd numbers, right? So let me say, how do I write odd numbers? An odd number is 1, which leaves a remainder of 1 when divided by 2. An even number is a multiple of 2. So it means it is 2 times something. Let's write it down. So the numbers are 2 times n is the even number, minus 1, that's the smaller odd number, and 2 times n plus 1, that's the bigger odd number. Right? And now let us see what this is. Now I know that addition is distributive over multiplication and so on, or maybe the other way around. Get how it goes. Multiplication distributes over addition. Right? So therefore this is 2n times 2n plus 1 minus 1 times 2n plus 1, right? Which is what? It is 2n times 2n, which is 2n whole square, plus 2n minus 2n minus 1. So this plus 2n and minus 2n, I don't care. The whole point is n can be any integer. You can take n to be 1, then you get 1 times 3. You can take n to be 2, you get 3 times 5. You can take n to be 17, then you get 33 times 35. You can take whatever value of n you want. You can take n to be minus 1, then you get minus 3 times minus 1. So you can take n to be positive, negative, 0, whatever. For every such value of n, this calculation makes sense. If I put in n equal to 1, I get 1 times 3 equals 2 times 3 minus 1 times 3 equals 2 square plus 6 plus 2 minus 2. So plus 2 minus 2 cancel. Minus 1. If I put n equals 0, I get minus 1 times 1 equals 0 times something minus 1 times 1 is 0 squared plus 0 minus 0. Again plus 0 and minus 0 cancel. Minus 1. So it doesn't matter that n looks like a symbol rather than an actual number. The rules of arithmetic that work for numbers also work for these variables. So you take any variable, let n be an integer variable, let's say, and compute. The whole point is, this is the point of using unknowns. they are equal to something. I just don't want to set them to be equal to something at the beginning. I will do my calculation and then say that, look, this works for everything. So I can now set it to be 1, I get that. I can set it to be 2, I get that. What is this? So what did I get? I got this is 2n square minus 1. Which means that if I add 1 here, I add 1 here, I add 1 here, even the minus 1 and the plus 1 cancels. And what do I get? I just get 2n square. So I started with a number minus 1 and a number plus 1, that same number plus 1, I multiplied them out and I added 1. And what I got was that middle number that I started out plus and minus, that middle number square. So in one calculation of basically 2 lines, I have used variables to not have to do this or this or this or this separately. All of this follow from this. I want minus factor is minus 7. Well, I put n to be minus 2. This is minus 5. Sorry, n to be minus 3. This is minus 7. This is minus 5. So if I put n to be minus 3 and just change everything. This is minus 7, minus 5. Here minus 3, so this equals minus 6 and it's minus 5. So you just put n equals minus 3 and change every symbol or every expression to an actual integer. You get this calculation just by doing this. Basically, I'm saying all of these calculations are exactly one calculation with variables in which I'm putting the different values for the variable and getting all these ones. So in a single calculation, we have verified all infinitely many calculations in this magic tree. And that's the point. You can also do this for 2 consecutive even numbers, and you can try that yourself. Write down the algebraic variable calculation that gives you 2 consecutive even numbers and add 1. And check that what you get is the odd number in between, perfect square. It's the same thing. Right? So this is the power of variables. Variables help us to not have to do infinite amount of work, but just do one amount of work and do infinitely many things at once. That's the real power of variables. And so that is what one uses to find the pattern. Okay, so let me now tell you about the pattern. So just for the 9s, the pattern for 9s. Rather, I mean, I know the pattern for 9s. I want to explain the pattern for 9s. And I want to do it again at one go. I don't want to verify separately the test for 9, the test for 19, the test for 29, or the test for 120. I want to do this for test for any number ending with 9 using the power of variables. So, okay, so say B is the divisor, right? Divisor is some number ending with 9. Now, how do you write down numbers ending with 9? Then it is some number, some digits 9, 8, 1, 0, 3, 7, 9. So it is this number multiplied by 10 plus 9. So let us call this as, let's say 10a plus 9. Okay. And now what was the pattern? We are claiming that the number k, whose powers we will multiply from left to right, is a plus 1. It is one more than the 10th digit or one more than the rest of the numbers. Why? So before I tell you the why part, let me now go back to Shakuntala Devi or Vedic mathematics. I think at some point I will erase this right. I'll erase a 19. 39, of course, is going to be 4. So the point is, now let me tell you that the test that I found, not just for 3, 9, it's not just for numbers ending in 9, but for numbers ending in anything, was already written down. So again, I was a high school student. It's not like I didn't expect anywhere the test to be not written down anywhere. It's such a fundamental and simple basic question that surely somebody has tried it before, and indeed people had. successfully tried it before, in fact. And this was found in the book called, let's see, uh, this test already existed. But of course, no, having grown up in an English medium school and so on, I was not aware of the test, and most people probably are not either. In the book, apparently, as far as I know, this book is called Vedic Mathematics. Published in 1965, so definitely before I was born. Yeah, by Sri Bharati Tirtha. Okay. And here is the way they describe the test in that book. For them, they call this number the K, whose powers I'm going to take. So they write down the exact same test. So Shakuntala Devi probably got the test from that book, because she writes down exactly the test that they did. Go from left to right, multiply the digits as you go from left to right by powers of a certain number, K, by whose powers one multiplies. The digits from left to right. From left to right, not right to left. Right to left is just powers of 10. That's called place value. Units digit, tens digit, and so on. But from left to right, one multiplies the powers, the digits by the powers of the number. What is that number? They call that number the Ekadika. What is Ekadika? किसी चीज से एक अधिक है, किससे एक अधिक है? The point is the following: you multiply the so एक अधिक of what? Namely, 10. So remember, what is 10? The whole thing, the entire number system that we work with and in this problem is in base 10. So 10 times, so what this number is, so for them, this is the definition of ekadika. Definition: K is ekadika, is the number, maybe the smallest positive number, maybe. Smallest positive number ten times which is ekadika of the divisor, of a multiple of the divisor. Meaning you subtract 1 from this 10 times this number, it is divisible by d. It's one more than a multiple that is the definition in basically in the Vedic math book, and that is the test that works. So let us check now. So maybe I'll check it here first, that it is indeed one more than that, and then about the smallest positive number, let me not get to it, but let's for example see here, right? So for 9, so 1. So what is 1 times 10? It is indeed 9 plus 1. What is 2 times 10? Right? This number is the ekadikas. The 10 times this number is one more than the multiple of that. It is 20 plus. Sorry, it is 19 plus 1. Here 3 times 10 is 29 plus 1. I'm not going to do 8 times 10. We all understand the pattern. Right? But now what I will do is, do I need to keep doing this for infinitely many numbers? No. I can just do this for the Once I know the pattern in general, see here my A is my variable, and once I know this for the variable A, I verify this for the variable A. So if D is this thing, A plus, so K times 10, but what was K? K was A plus 1. And what is A plus 1 times 10? Multiplication distributes over addition, so it is 10A plus 10. What was D? The divisor was 10A plus 9. This is exactly D plus 1. So that's exactly what we are doing here. K times 10 is D plus 1. And that's exactly what we have. So this is the pattern in general. Okay. So the test works because basically I'm doing the Ekagita. So I'm basically using the Vedic math test, and that's exactly, or my test is the Vedic math test, the one that I found, and it is exactly the same test. This was even written down. It was written down in this book in 1965, but that means it was there in Vedic math centuries ago. I did, but again, we are slowly starting to discover what all people have done in the past. So at least something as basic as divisibility test was very well understood in India already. Somehow it wasn't written down anywhere in the West either. This is why when I wrote the paper, I wrote my findings into a research paper kind of thing. Obviously not a serious level research journal, but an undergraduate, college level research journal. They publish such things by, say, enthusiastic high school students or enthusiastic college students. And so they published my paper in 1997. But so just from tinkering around in the summer holidays in a notebook with books and so on, I was able to get this thing. And this really comes back to this really comes back to this pattern that it's a study of trying to find patterns and then trying to understand why they were, trying to generalize, distill the common thing in the pattern. What is the common pattern? This is the common pattern. If I call this number as 8, then it is 10 times A plus 9, and from that I'm seeming to get this thing that works here. Now, and then you put that together into a common pattern, try to then prove. Now in mathematics, it is not empirical data, one has to actually provide a proof. So there's a difference between data-based research and mathematical research, theoretical mathematical research. One has to find the proof. So then I had to prove this thing, and there is some, the basic tool used to prove this is to use congruence modulo. So congruence modulo kind of mathematics, and I don't think I have time to do that here. That kind of arithmetic, but that does work out, and once that works out, then you can prove this result. Maybe one small thing I should mention is it is the smallest positive number 10 times, which is one more than the multiple of D. Right? So fine, when we found such a number and so on, you can prove it's the smallest. But the first question is, why should such a number exist in the first place? Maybe there is no such multiple. Maybe 10 times, maybe every multiple of 10 is not a multiple, is not one more than a multiple. So that's the one thing I will say, and I suppose that's probably enough for me to stop, right? We are at, I don't know what time, but yeah, maybe I'll stop. So maybe the last question to discuss is why is there always a multiple of 10? That is one more than the multiple of D. And then the smallest such multiple is what I called my Ekagita, right? So, and this is a very valid question because in fact, it turns out that this statement is not true. Always. It is not true for, say, if I have an even number. Right? So suppose my D is an even number. Suppose my D is like 2. Then every multiple of 10 is also even. D is also even. So their difference cannot be 1. The difference is an even number. 1 is odd. So it's not always true that this happens. And that's the whole point here. So this is a test that was there, but there was one caveat, which now I will tell you, and then we will stop. This test already existed, and this existed for B, the divisor D. See, I put 9, 1, 3, and so on. These numbers have one thing common as far as looking at 10 goes. None of them are odd or even, and none of them are divisible by 5. Basically, they share no prime factors common with 5. So for GCD, the greatest common divisor of D and the base in which you work. Our base is 10, we use base 10. So basically. But actually, this whole test, including in the Vedic math book, was for any base. You can work in binary base. You can work in hexadecimal base. You can work in base 12. Then this 10 would be replaced by 12 or 2 or whatever the base you have. For whenever these two numbers are co-prime, D and 10 are co, then this is the test. And so now this is true when, so now I should therefore add the caveat here. Why is there always multiple of this thing? Provided D is co-prime. D is co-prime to 10. Which is the same as saying that a GCD is 1. Why should such a number exist? And the answer basically is it exists because another way to write down the GCD, mention the answer and then we can start. Because the GCD of any two numbers, not just 10 and B, but of any two integers, can be written as something like alpha A plus beta B. You can always write it as some multiple of A plus some multiple of B. Alpha beta are integers. So in this case, so you have 1 is the GCD of D at 10, meaning D is co-prime to 10, then this is equal to alpha times D plus beta times 10. And now I can take the smallest beta positive. So alpha is, you can think of alpha as negative and beta as positive. And I can take the smallest beta and the smallest as beta. So what I know is because these are co-prime, there already exists such integers. There is an alpha and there is a beta such that this equal to 1. And now the moment I just take the smallest as beta, so that maybe I will say let K be the smallest as beta. Then what do you have? And just write this equation down. Then we get 1 equals alpha times D plus K times 10. Which means K times 10 is minus alpha. Alpha was negative anyway, so minus alpha is positive. So here we go. It is the smallest positive integer, which is 1 more than a multiple of D. That is what the test said. So this test works when D is co-prime to 10, because then another way to write this down, one has to check why this is true, but it's true. Another way to write down the GCD, the greatest common divisor, is as a linear combination, as some multiple of A plus some multiple of B, or some multiple of D is a multiple of 10. And that's exactly what Ekadeka gives you. Okay, so I think I should stop here. But the idea basically again is that there are patterns, and mathematics for me at least is all about finding patterns. You find patterns in basic examples. You start doing n equals 1 case, n equals 2 case, n equals 3 case. Find a pattern, then try to prove them. Then formulate a hypothesis and then prove the hypothesis. And even now, I started doing mathematics this way 30 years ago in Indore, and I still continue doing mathematics, I think, the same way. It's first I need to find enough data to build some intuition in my head, to find some hypothesis. And then after that, I am able to do some mathematics that prove some theorems and so on. Okay, I think I'll stop.
Thank you, sir, for enriching session and informative oration. Now I request to dignitaries, if any query, to ask questions. And dear attendees, put your questions in chat box.
There is one chat. Literature reference related to this topic. I would say you can study basic things like modular arithmetic, for example. I don't know what to say. You can read textbooks or books on modular arithmetic. Maybe I don't even know what to say. Maybe something like problem. This may be a bit advanced. This is one book that I know about. The others, but you can just maybe even on Wikipedia. On Wikipedia, look at
Okay, sir.
on the internet. So basically, just the words modular arithmetic should give you examples of this the tool that one uses to prove. Basically, it talks about the remainder that is left when you divide one number by another.
Any questions from dignitaries?
Hello.
Yeah.
Yes, sir. Actually, it's just a simple question that I want to know. What is the present scenario? I mean, in the field of research, uh, are there any research papers dealing with such problems as you have discussed? For example, the divisibility of numbers. So, yeah, I want to know what is the present scenario because I'm not from number theory or algebra.
Right. This one, as I said, even I did in my thing, but it was already known in this textbook. So divisibility of numbers is definitely done already.
Okay, 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 okay. Thank you, sir.
Any questions? Sir, can we conclude? Satish, sir, can we conclude? Thank you, sir, for sharing your great knowledge with us. It was a great pleasure to all of us to listen to you. Thank you once again.
Thank you.
Now I request co-coordinator of program Dr. Shobha Jain, Shri Vaishnav Vidyapit Vishwavidyalay, to propose words of thanks.
Thanks, ma'am. Good afternoon, everyone. Our seventh Srinivas Ramanujan oration is getting over. It's my pleasure to deliver the words of thanks. Very special and heartfelt thanks to our distinguished speaker, Dr. Apur Khare, Faculty of Mathematics, IISc Bangalore. It's really an opportunity to listen him on divisibility test. We feel honored to have him with us. I express my gratitude to our Vice Chancellor, Dr. Upinder Dhar, for providing directions and encouragement for Srinivas Ramanujan Oration series. And today was the seventh one. Such program will go a long way in building the character of our university. I extend my heartfelt thanks to Dr. Santosh Dhar, Dean, FDSR, Shri Vaishnav Vidyapit Vishwavidyalaya, Indore. Her participation is creating an environment where academic grow. I recall an inspiring quote: mathematics may not teach us how to add love or subtract hate, but it gives us every reason to think that every problem has a possible solution. And we also would like to thank and acknowledge our gratitude to all HOIs, HOD, registrar, faculty members, and students of SVVV for being part of this oration. Thank you.
Dr. Ghare, I was the colleague of Dr. Praveen Kekre.
Okay.
Uh,
That's nice. Hopefully, I will see him the next time I come to Indore. I met him the last time. Yeah.
Thank you for joining us.
My pleasure.
Thank you, ma'am. Thank you, sir. Now I request all the rise for national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, sir. With this, we come to the end of session. Thank you all for your participation. Thank you, sir.
Dr.
Thank you,
Khare.
sir.
Thank you very much.
Thank you very much, Dr. Khare. I'm really very thankful you have joined us and given your important time.
Yeah.
So thank you very much, sir.
Thank you. Thank you.
Thank you, sir. Thank you very much.
Thank you.